Hello and welcome. So let's get back into a discussion of infrared spectroscopy. So let's summarize what we've been working on for the last lab period or so. So we have vibrational frequencies for molecules are usually greater than about 1,000 wave numbers. So this is going to correspond to about 3 kcals per mole needing to be absorbed to vibrationally excite a molecule. And we found very few molecules exist in a vibrational excited state at room temperature. And so then we also found for most molecules, B is sort of on the order of, maybe about 2 to 20 or so wave numbers. And this is going to correspond to about 30 calories per mole. But there's this degeneracy factor, 2J plus 1. And this degeneracy and the relatively small energy difference it takes to rotationally excite molecules makes the most occupied state not J equals 0 for most molecules at room temperature, more like J equals 2 to 3 to 4, depending on the particular value of the rotational constant. So another consequence that we see in spectroscopy is that only certain transitions are allowed to be observed, and we can only observe transitions from states that are actually occupied to begin with. So whenever we think of infrared spectroscopy and the spectrum we're going to see only transitions from those states that are originally occupied by molecules and then to other states through allowed transitions. And so if we look at and consider the first couple of vibrational energy levels for a molecule, let's come back to the idea of a molecule being harmonic versus rigid. And so the harmonic behavior would say that if you take the difference of energy from J equals 0 up to J equals 0, from V0 to V1, compare that to the energy it takes to get up to V2, that the energy difference here between J0 and J0 would just be equal to hν. And then the same difference from J0 to J0 from V1 to 2 would be another hν. And so we would have this parabola shape describing the harmonic behavior, and the rigid behavior would describe that we go from 0 to 2 to 6 times the rotational constant up to 12. And so when we look at real molecules, though, we see, or let's point out that the harmonic and rigid rotor approximations would show identical energy levels for the rotational energy level spacings in V0, V1, and V2. Now what we might want to do is compare that for real molecules. Of course, we discussed non-rigidity. Non-rigidity can be explained by the lengthening of a bond through rotations. So as the molecule begins to rotate more and more, with more energy, the bond is lengthening along the way. And then you have this energy for, say, the J1 state of not being 2b, but being 2b minus 4 times d. And then when you go up to J2, this would be equal to 6b minus 36d. And so you have this d times j squared times j plus 1 squared. Then it's even more pronounced. It's, for the J3 state, it would be equal to 12b minus, now it's 144d. If you take the 3 squared, which is 9, plus 4 squared, which is 16, so 9 times 16 is 144. And so you can see that this is leading the rotational energy levels to be a little lower than where we predicted them from, and it's going to become more pronounced as you go up in rotational, go up in the rotational quantum number. And so then the non-rigidity, though, doesn't quite explain the difference of the rotational energy levels for the for the V equals 1 and the V equals 2 energy levels. And so to really understand the appropriate spacing of the energy levels in V1 and V2 being more compressed, what we have to come back to is the fact that the molecules are behaving anharmonically and non-rigidly. So the anharmonic behavior is the stretching of the bond as it's vibrationally excited. And as you stretch a bond, as we saw the connection with the rotational constant, is that it changes the moment of inertia. You change the moment of inertia, you lower the rotational constant. And so then if you lower the rotational constant, then you decrease the energy it takes to rotationally excite your molecule. So if you change the bond length from V0 to V1 to V2, then you're of course going to change all of the energy level spacings of the rotational energy levels in those vibrational states as well. And this is, showing it maybe a bit more dramatic than what it truly is, but your energy levels are becoming more compressed as you go up in vibrational energy level, simply because you're lengthening the bond and decreasing the rotational constant as a result. And so this is kind of now comparing the difference between a harmonic rigid rotor model to our non-rigid rotor model, but still harmonic. Notice that the J0 to J0 differences are equal, so this would just be h-nu to here, and another h-nu up to the v equals 2. And then when we see the anharmonic model is where we see that the energy here is really not equal to h-nu. We have the anharmonic frequency, and so the anharmonic frequency is becoming more pronounced, and the vibrational energy levels are becoming more compressed as we go up in vibrational energy state. And so now the one thing I want us to take away from this point here is that some terminology is that we might describe the spacing of the rotational energy levels in the v equals 0 state by their B0 and D0 values. The B0 and D0 would be the rotational and distortion constants for the v equals 0 level, and then we describe for the v equals 1 level of having a B1 and a D1. So the B1 and D1 would be the rotational and distortion constants for the v equals 1 level. They're going to be a little bit smaller, of course, as we're more compressed, or at least the B value will be more compressed, smaller. And the same thing for the v equals 2 state, for B2 and D2 describing those spacings in the v equals 2 level. And through the observation of the infrared spectrum of HCl, we can actually determine and calculate from the spectral absorbances, we can calculate the B0 D0, the B1 D1, and the B2 D2 values. Okay, so from this simple spectrum here, what we might do, and this is actually one of the tasks in your handout, is just labeling a spectrum. This is one way to look at a spectrum. I think the one in the handout looks a little bit different than this one, but just think of your spectrum as having a high and a low energy side. High energy is high wave numbers, low energy is low wave numbers. Their wave numbers is, think of it as an inverted wavelength. And so if you think of energy of a photon as it relates to, say, h-nu or hc divided by lambda, if a wave number is a 1 over lambda, an inverted wavelength, then energy is simply directly proportional to the wave numbers. It's just like it's directly proportional to frequency. And so our high energy side here, our low energy side here, that'll help us make sense of our two different branches that we'll get into in the next slide. So as we look at our molecule from v equals 0, this is where most of our molecules are going to exist, is in the v equals 0 state, and one of the various rotational states for HCl, I think we saw that we're going to get some reasonable population, say 1% of the sample will exist within probably about J equals 0 to J equals 10 to 12 at room temperature. So let's kind of focus on those transitions from the lower rotational states and then consider what transitions are allowed up to v equals 1. And there's really two key selection rules. One of those is that we have to go up by one vibrational quantum number. That's going to be our most intense transition. We're going to call it the fundamental band of HCl. And then one of the primary branches is going to be the transition that has delta J equal to +1. And so that's going to start, so imagine we have a molecule that exists in J equals 0, V equals 0. It can go up to V1, but it has to jump up by one rotational quantum number. So it has to excite up to the J equals 1 energy level and V equals 1. And then if the molecule originates, though, in J1, it goes up to J2. So it has to go up by one rotational quantum number as well. And so we have our R branch defined as the set of transitions that go from some low J value to some high J value. Now let's contrast that to the other allowed set of transitions. That's the delta J minus 1. So the delta J minus 1 transitions are where we start in, say, 1 and end in 0. Start in 2, end in 1, start in 3, end in 2, start in 4, end in 3, etc. So these are our P branch peaks. So our R branch peaks, our J goes up by 1 from where we originate as we go up in one vibrational quantum number. And then we define the R0. The 0 is defining the initial J value from the original occupied state of our molecule. And so likewise, the P transitions are the delta J minus 1 transitions, where we go down by one rotational quantum number. So starting at 1, going to 0, 2 to 1, etc. Now notice, of course, there's no P0. There's no P0 because for there to be a P0 would mean we'd have to have a negative J state. And of course, we don't have negative J states. The lowest J can be is 0. And so one other transition you might note, this is kind of an interesting observation to point out, or lack of an observation to point out, is that there's no Q branch. The Q branch would be, let's do this one more time. So the Q branch would be the 0 to 0 transition, or the 1 to 1, or the 2 to 2. And what's really interesting for diatomic molecules is two things. One is that the molecule has to be polar if it's diatomic in order to absorb infrared light. If you're comparing like O2 and N2, as we take an infrared sample, we're not going to see any signatures for O2 or N2 in the IR region because they can't absorb the light, because through the absorption of infrared light, you have to have a change in dipole moment for any molecule. But for a diatomic, you can't change a dipole moment if it's a homonuclear diatomic molecule. But the other thing that's really interesting to point out here is that this Q branch is not observed, whereas for most bigger molecules, if you look at most organic molecules, this is really the more intense peak, is that Q branch. And so if you can imagine, for a diatomic molecule, what we have is a relatively low probability of absorbance of light through the P and the R branch transitions, where most organic molecules would have very intense Q branches, and then these P and R branches would be not so intense. So when you think of looking at your OChem notes and reviewing where different functional groups absorbed, what you're really seeing there is an intense Q branch that, because one of the things that you may get a little bit confused by here is why the infrared spectrum looks so different here for something like HCl. The issue here is that we have a gas phase molecule, or a molecule that exists in the gas phase, and we're seeing really fine resolution, and then we're also seeing some types of transitions that we tend not to observe commonly for our larger molecules in the way we take our infrared spectrum. But so let's compare the relative energies of these transitions. You can kind of see that on our vertical axis is energy, that as we go up in rotational energy, you see that the energy levels are going to an ever-increasing energy level, so that the R branch peaks are relatively higher in energy compared to the P branch peaks. The R branch peaks are always starting in a low J going to an even higher J. Of course, the P branches are starting out in that higher J and ending in the lower J. And so since the rotational energy levels are not equally spaced, we get this divergent behavior, this divergent amount of energy for the transitions here. And so if we think of just like taking these vectors and aligning them, you can kind of see that the P4 peak of these shown would be the lowest in energy, whereas the R3 would be the highest in energy. So just note this general trend. As you go to a higher J, as you start out in a higher rotational energy level, and you do an R branch transition, a delta J plus 1, you go to a higher energy. And if you go back to the P branch, start with the P1, that's going to be the highest energy P branch peak. And as you start out on a higher J, you're going to then transition to a lower amount of energy being absorbed. So we're getting, building towards is this branch behavior that we see in our HCl spectrum, that we see, a high energy branch. Now, again, notice that the wave numbers are kind of reversed here. So our high energy branch on this spectrum here is on the left side. So you have to note, okay, what's my unit? How does it go? So we got 3100 here, 2600 here. So we have the high energy branch here. So this is our high energy R branch, and then this is our low energy P branch. So this would be the P1, because our first P branch peak going to a lower energy to the higher P value. And then here's our R0, and onward. Okay, so you can actually use this spectrum here to get some of the data you need to make some of your tables. And then on the next slide, we have the overtone. Now the overtone is just the direct absorbance from, a V equals 0 molecule in the V equals 0 state to the V equals 2 state directly through the absorption of a single photon of light corresponding to the appropriate energy for that transition to arise. Then you have the same P and R branch arise. And so you have an R branch peak for the J0 to J1, the J1 to the J2, for V0 to V2, but notice the probability here is lower, so the intensity is a lot lower for this particular branch here, or for this particular band. So we would call this the first overtone band of HCl. If you notice in the previous slide, we're at around 3000 wave numbers. We're a little less than that here. Of course, it would be exactly double. If you looked at the R0, we would be exactly double this if the molecule were perfectly harmonic. So you can see we're not perfectly harmonic. Okay, so what you can do with the fundamental band, and we can go through some of this in video format to help you get through the calculations. Well, we can solve for B0 and D0, B1 and D1. We can solve for B2 and D2 using the overtone band. And then from some of the transitions, we can also determine things like the fundamental vibrational frequency, the overtone vibrational frequency, and then from those determine the harmonic and the anharmonic frequency for HCl. Okay, so I think that'll take us through this video, this spectrum here. Let me just point out this is showing a sample of DCl. So if instead of having HCl in a gas cell, we instead have DCl, deuterium chloride, you see a change in the absorbance due to the different mass of the deuterium atom. And deuterium has a double the mass approximately compared to hydrogen atoms. So this has a big change on the observed absorbances. Okay, so that's all for this video. Thank you for the attention.